Hello.
Hello.
How
Hello,
are you
I'm
doing?
Kyung-seok. Nice to meet you.
Hello, I'm Rodolfo. Nice to meet you too.
Nice to meet you. Yeah. So may I'm not sure whether Professor Katzarkov here or not.
You
So
are no co-host, right?
pardon?
You are not host and co-host in this.
Yeah, I think.
Yeah, you are now. Yeah, they have made you.
Okay, thank you. So yeah. So you are in Miami now?
Yes, I'm here in the office now.
Oh, I see. You are in the office.
Yeah.
Oh, I see. Yeah.
So can you see it all? This. Can you see the
Pardon?
screen?
Yeah, I can see the screen. Yeah. So can you wait something like 1 or 2 more minutes?
Yeah, no problem.
Yeah, people can join and then maybe 1 minute, then start. Yeah. Okay. Okay, so shall we start?
Yeah.
So, yeah, sure. Okay, let's start. So it's my pleasure to introduce Professor Rodolfo Aguilar. So he will talk about quantum representations and the Bogomolov-Katzarkov surfaces.
Okay, thank you for the introduction and for the invitation. So let me tell you the content of this talk, how I will divide it. It will have 3 main parts. I will start with some preliminaries. Then I will state a theorem and some corollary, and then I will give you some tools to prove this theorem. So the work that I'm talking about is a work of Eyssidieux-Funar, and they are around some special surfaces that I will try to describe now. And so they were supposed to be counterexamples to some conjecture. And in this paper, they prove that they are not counterexamples, and they use this quantum representation. So this is the main tool that they use. Okay, so let me start from the beginning. I will need to define what is a holomorphically convex manifold. So I will start with a complex manifold, and I will take a discrete sequence of points. Then if for any discrete sequence of points, there exists a holomorphic function, which is unbounded on this sequence, then we say that the manifold is holomorphically convex. Okay. So for example, if we have a compact manifold, as we cannot have any discrete sequence of points, so it is automatically holomorphically convex. So the main case of interest is when it is not compact. So now we can state the Shafarevich conjecture on holomorphic convexity. It says the following: if we start with X smooth projective variety, then this conjecture predicts that its universal cover should be holomorphically convex. It satisfies this property. And in the case of curves, for example, it is a corollary of the uniformization of Riemann. And actually, I think this was the motivation for Shafarevich to stating this conjecture. So now, after the case of curves, there were some work around this topic in the case of surfaces. So it started around mid-80s, and they continued with some special case of surfaces, and then it was extended by Eyssidieux to higher dimensional and some restriction on the fundamental group. And as we know, the fundamental group is quite related to the universal cover, so it's kind of natural to impose some conditions on it.
Excuse me, could
Yes.
you go back to the previous slide?
Yeah. No.
So, I mean, may I ask you what happened? X is simply connected.
If X is simply connected, then
yes, smooth projective
yeah. Then its universal cover should be X itself, right? So
yeah.
As it is compact, it is holomorphically convex, so it's okay.
So I mean, you know, so when X is smooth projective, I'm sorry, maybe I'm it's very stupid question, but if X is smooth projective variety, which is simply connected, then as you mentioned, the universal cover is X itself.
Mm-hmm.
Then the only holomorphic function on it is the constant function, isn't it?
Yeah, but we cannot have any discrete sequence of points. So it is holomorphically convex by, let's say, by empty condition, something.
I see. So I mean, okay. Thank you very much. Thank you.
No problem. Yeah. So now, one of the strongest theorem that we have today is the following theorem of Eyssidieux-Katzarkov, Pantev, and Ramachandran that says the following. If we have an X as before, suppose that the fundamental group has a faithful representation in some GLN for some n, that is the fundamental group is linear, then X satisfies the Shafarevich conjecture. Okay, and it was later extended to the compact Kähler case by Eyssidieux, Campana, and Clodon, but this is one of the strongest that we have theorem in this area. So now it seems difficult to extend much more this one. So the next question should be, can we find a counterexample of this? Is this always true? So in view of this theorem, we need to find some group that is not linear. And there are known some nonlinear groups in algebraic geometry. Maybe the most famous are non-residually finite, whatever that means, but there exist. So in the late 90s, Bogomolov and Katzarkov constructed some examples of smooth projective variety surfaces, and they suggested that these surfaces could be counterexample to the Shafarevich conjecture. So these surfaces were related with some group that is like a Burnside type group, and it relied in some conjecture of Selmanov that they are not residually finite. So everything was conjectural here. So now let me try to review the construction of these surfaces. But now I will use the language of Eyssidieux-Funar. So I will not use the original construction of Bogomolov and Katzarkov. So I will start by defining what is a root stack. Then we will need this construction. So we'll consider X a smooth stack. If you don't know what a smooth stack is, you can think in a smooth variety. And then we can consider D a normal crossing divisor in this stack with Di its reducible components. So I will fix a P in n to the power n that is equal to PPP. And then there exists a smooth stack that I will denote by P over this divisor, called the root stack, that satisfies the following properties. The stack underlies a variety called moduli space, and it has the same moduli space as X in this root stack. And it is universal between the X stack for which D pullbacks to P times another divisor. So essentially, we can think of this stack as classifying the ramified coverings in X that ramifies exactly over D. And so, for example, if we can see this stack as a global quotient, and we have a variety over it, in a finite group acting on it, we will have ramification exactly above the divisor D. So this is the idea of this root stack. And Eyssidieux-Funar will apply this construction to the moduli of curves. So we will need to review the divisor at infinity of the linear Mumford stacks. So we will consider the compactification, the linear Mumford compactification of the moduli of curves and the moduli of stable curves with one puncture. So the linear Mumford showed that if we consider the divisor at infinity, let's say, then it consists of the integer part of g over 2 plus 1, and moreover that it is a normal crossing divisor. It's not simple, but it's normal crossing. And then Knudsen showed that if we do the same for the universal curve, then we will have G divisor. Not the notation that I will use. I will use D for this divisor, and I will use D1 for this other. So I will be using this. Please recall the notation. Okay. And then I want to make this root construction over it and relate it to a fundamental group. And for this, I need to introduce the mapping class group. Recall that this mapping class group is the group of orientation preserving homomorphism that fix this set of market points if we have n market points in a surface of genus G. And we need to take modulo isotropy. So we have a proposition of Den. He showed that this group is finitely generated. We would only need two cases for n equal 0 and for n equal 1. And for n equal 0, we need the integer part of g over 2 plus 1 special generator called the Den twist. Recall that the Den twist is fix a simple curve. You put a cylinder around it and you twist once around the curve above. So note that this number for n equals 0 is the same number as the number of irreducible components that we have here. And for n equal 1, we have G. That is precisely the number of divisor that we have in the universal curve. So now I will introduce some subgroup of this that is going to be quite important for us. And I will denote by mode sigma Gn P, the subgroup of the mapping class group generated by the P powers of the Den twist. So I will take every Den twist and I will put it to the P power, and then I will take this generated by this thing. So let me say that this mapping class group was generated by the Den twist, and if I consider this to the power P. So this is one type of, well, if I make the quotient of this by this, it's following the idea of Burnside type group. It's not exactly the verbal quotient by all words to the power P is equal to 1, but it's keeping this idea. Okay. So now, as I was saying, if we consider these root stacks, we consider the root construction, but for the moduli of curves and moduli of one-pointed curves with this divisor, we have a first proposition of Eyssidieux-Funar. And it says the following: the fundamental group of this stack, the first one, is this quotient. We quotient the mapping class group by this subgroup when n equals 0. And we have a similar proposition for the fundamental group of this stack but when we mark 1 point. Okay. So okay, any questions here? Okay, so once that we have this, we can review the construction of the Bogomolov-Katzarkov surfaces in this language. So what I will need a fibration that factors over the moduli of curves and over the universal cover. That is the idea, and the formal thing is I will take a non-isotrivial fibration with S as smooth projective surface onto a smooth projective curve C, such that P is a projective morphism with connector fibers. The generic fiber is a genus greater or equal than 2 curve, and the singular fibers are stable curves. So in particular, they are reduced, and the singular consists of ordinary double points. So we will have a commutative diagram going like this. Knudsen proof that this mg1 bar is the universal cover of over g bar. So we have a factorization in this. And for the Bogomolov-Katzarkov surfaces, we will use the root construction that I made before. So I will make the root construction for this, and as they have a map to this, we can make a fiber product. I will describe this more precisely later. Just let me tell you that this commutative diagram will induce some other commutative diagram in the following way. Recall that we have seen this construction that was the root stack construction over this divisor, and we can have now a surface like this that is obtained by a fiber product as follows. So we will define this surface as we saw it. It has a map over the mg1 bar, and this root stack, it will have a map also to mg1 bar. And I do the same fiber product construction with the curve, and I will obtain a diagram like this. So what is this saying? The original construction of Bogomolov and Katzarkov was as follows. We consider a fibration such that in a covering of this curve C, a ramified covering that ramifies over the image of the singular fibers with ramification P in all points. So then we consider the pullback of this surface, and it has some singular points, and we need to resolve the singular points. And then this surface was the Bogomolov-Katzarkov surface. But here we can encode all this information into stack information. In the base, we can start in, as this root stack is codifying the ramification. This is as follows. This C intersects the divisor at infinity precisely when it has some image of a singular fiber. So we put some weight, some isotropy P in this point that intersects the boundary, and this surfaces has isotropy exactly at the boundary of this curve as well. So we are putting some, this essentially is like making the root construction in the surface in the singular fibers. We are putting weight P to all singular fibers. But what we really need here is that they have a map to this, because we will find some representation of the fundamental group of this, that the restriction will induce some representation in this surface. Okay. So now let me tell you about the structure of this surface. What is really important to us is that it will have some exact sequence of groups. So this map can be seen as a fibration in the stack setting. They will have a smooth curve of genus G as a general fiber. And then we can have a short exact sequence, as in the case when we have a fibration with smooth fibers. And this IPC is the image of the fundamental group of a generic fiber. Recall that this is the fundamental group of a curve into the fundamental group of the stack. And now we can have a more precise description of this group. And this group is the quotient of the fundamental group of the fiber by the elements C to the power P, where this CP is a family of homotopy classes that are invariant under the monodromy. So you see, we have seen a kind of related construction in the mapping class group to some elements to the power P. And here we see again this kind of construction to some very special family. Okay. So now let me state this proposition that was proved by Bogomolov and Katzarkov, but in the language of Eyssidieux-Funar. So if P is odd, then this surface, this orbifold surface, is the quotient of a smooth projective surface by a finite group, a global quotient. So in the orbifold words, it says that it is uniformizable. So we were interested in the fundamental groups of complex projective smooth varieties, and this tells us that we don't go out of this world. We don't enter into the stack world or into the singular world. So we really stay there. Okay. So as you can see, this group is the one that was complicated, the one that is expected to be non-residually finite by the conjecture of Selmanov. And what I know is that they didn't know any representation, infinite representation of this group. And this is precisely what quantum representation does. They give us representation with infinite image of this kind of groups, and then using some result of, well, the main theorem that I stated before, the Eyssidieux-Katzarkov Ramachandran, they can prove the holomorphically convexity of this kind of surfaces. Okay, now let me review the Biermann exact sequence for the mapping class group, and we will see how it fits in our language that we are now introducing in this old quotient stuff. So what does this Biermann exact sequence does? It relates the mapping class group of the genus G curve with one puncture to the mapping class group of genus G only. But it also relates to the fundamental group of it. So we have a point pushing map. When you have a simple curve, you can like push around it and you will obtain a homomorphism preserving the orientation. So you will have a map here. And then recall that the F1 map was the map from the universal curve to mg bar. This map will induce some map in the root construction. Okay, so we can see again this as a fibration, and we can take the long exact sequence of the homotopy of a fibration, and we will obtain something like this. I don't like this notation, it's like kind of bad, but we have a very nice notation. Recall that by the proposition that I showed you before, this group was isomorphic to this quotient, and this group was isomorphic to this quotient. Okay, here BT is the quotient of G, of this fundamental group, by all the powers P of a simple loop in the fundamental group. Before, in the Bogomolov-Katzarkov surfaces, we have only some family here. But now we have all the simple loops. I can also denote this group by this notation. This is the notation of Funar, and this is the notation that Bogomolov and Katzarkov used. But so I think it's better to see it in this way. Okay. So what do we obtain if we put all together? We obtain a diagram as follows. So in the first row, we obtain the short exact sequence of the Bogomolov-Katzarkov surface. And in the second row, we obtain this the exact sequence that I just showed you. So once again, if we could construct a representation of this group that is very well behaved under this kind of maps, and we can see that these have infinite image, then it will restrict to this subgroup. Okay. So let me now pass to the second part. So this is all the preliminaries, kind of long story. And now, let me tell you one of the main theorems in the Eyssidieux-Funar paper. We denote this as PP, the surface as above, and we will denote by E the inclusion of a general fiber into this surface. So one of the main theorems is that there exists a complete finite dimensional representation of this surface, such that if we restrict to the fiber, then this representation has infinite image, and moreover, it contains a free group in two generators, so it's quite big. Okay, and for the following, we will have some holomorphic convexity, not of the universal cover yet, but of some infinite Galois cover. So let me make the statement here. If we consider G to be greater or equal than 2 and P bigger or equal than 5, and we will consider this odd. In what follows, we will consider only the odd case. If I have the results, if I have time, I will consider the case even, but first the odd. Then this surface will admit a holomorphically convex infinite Galois cover. And then I will make some notion for the experts. So this Galois cover will have the property that the codomain of the Cartan-Remmert reduction is two-dimensional. And this will be one of the first steps into proving that the universal cover is holomorphically convex. So let me make a sketch of this proof. In this paper of Eyssidieux-Katzarkov, Pantev and Ramachandran, they constructed a holomorphically convex ramified covering of any projective variety that you have. In this particular case, we will apply it to this construction, and the construction is as follows. You consider the universal cover of the variety that you are considering, and then you quotient by the action of Hn, which Hn is a group where you consider all the representations of the fundamental group to some GLN with n fixed, and you intersect all the kernel of these representations to make this quotient, and this is holomorphically convex. Well, they show that's the main theorem. And then as it is holomorphically convex, you can have the Cartan-Remmert reduction. This reduction gives you a Stein space whenever you have a holomorphically convex one. And then you will have an action of this group, of this quotient, P1 of the surface over Hn, acting here and here and you can make the quotient by it. And this will give you what it's called the Shafarevich morphism. This is a morphism from the original surface to some Shafarevich space. And now this has the following property. When you have that all positive dimensional irreducible subvariety set of the surface that we are considering, then if we consider the image of the normalization of the fundamental group of the normalization to this quotient, and it is always infinite, then this Remer-Cartan reduction is the identity. And by definition of this, or by the properties, then this UN is Stein. So in particular, this is, if it is a Stein, it implies that it's holomorphically convex. And if we have this property, then this, the universal cover of Stein, and then we obtain the holomorphic convexity. This is not exactly the case yet. This is gonna be true only for a general subvariety. And when this is true for a general subvariety, the dimension of UN equals 2. And this is precisely what the statement here is saying. The way to prove it is that we have, if we have a general surface, a general irreducible subvariety like this, we consider the image of the fundamental group in the base, in the curve, and it has an infinite representation image. But if this doesn't work, that means that the surface is in that the subvariety is in the fiber. And if it is in a general fiber, we use the theorem before, the main theorem. So if it is in the fiber, then we have a representation with infinite image. And well, for general, of course, they will have infinite image. In the only case that rests is that they lies in the singular fibers. And then it's the proof of this theorem. And then they also go further and they prove that they actually this case is true. The universal coverage is just time. I will make a pause here. I know that it's very specialized, all of this, and it should be hard. Do you have any question here before I go to the second part of the talk? So if not, I will review. Yes, do you have something?
So could you, I mean, maybe you already explained this one, but could you what is, I mean, anyway, what is the benefit of introducing root stack? Anyway,
the what? Sorry.
So I mean, what is the benefit? I mean, anyway, you how can I say, in compared to previous result, what is benefit of introducing this root stack in this case?
I didn't get it. Compared with what is the use of the root stack?
I mean, yeah. So I mean, how can I say? So I mean, you use this root stack. I mean, so how can I say? This using this language of root stack is essential in this context.
Okay,
or
okay, I see.
Everything
I
can be done in classical language.
Yeah. I think the one, I don't think it's essential. I think what it makes clearer this this relation. I mean, as we are considering this, well, we haven't seen yet where this representation comes from, right? I mean, we have used this theorem, but the representation will come from this group. And then using this language of stack, we will have this diagram like this, right? And we cannot have a diagram like that, I think, in the usual sense. So that's why I Like this is just a language that they kind of use to rephrase. I don't think the really important part is here. That's why I put it like preliminaries. So the really important part is the representation that they use, the representation and the properties that it has. But I think the language just make a clearer way, or I mean, it's difficult to get when you are not used to it. But then one that you kind of understand the idea, if not the details, they make clear this construction. Where do they come? What is the relation? But I don't think it's essential.
I see. Okay. I see. Thank you very much. Thank you.
Problem. Okay, so I will review this.
I'm sorry. One more. Yeah. May I ask you one more question?
Yeah, sure.
Why you need this p is greater than equal to 5 condition?
Sure. That's important. Yes, we will see later that. Well, here we were stating that it has infinite image, but of course it relies in this representation, and we will actually see that in the next part, this representation will have finite image if p is lesser than 5. So that's why we really need the infinite part here. If we have infinite image, then we will have an infinite cover here. And if not, it is just going to be a finite cover. And well, that's compact. Okay.
I see. Thank you.
Yeah, I hope it becomes clearer here.
Yeah.
So let me now try to give an idea of what a TQFT is and which one they use. So a TQFT, very roughly speaking, is a functor from a category of coverdism to finite dimensional vector spaces, plus some axioms. But let me be more specific about this category C. It will consist of orientable closed surface with colored banded points. So what I mean with this, banded points will mean a point with a tangent vector, and colored will mean that we will put some information in these points. So here we will put just some numbers, but it can be other things depending on which TQFT we are considering. So what are the morphisms in this category? They are oriented coverdisms. So coverdism is a 3 manifold. We are considered here a 2 manifolds in the real dimension, and such that the boundary has 2 surfaces in the objects. Well, we take it to be oriented, and this is the morphisms. But moreover, we are going to decorate these coverdisms with a graph and some information in the graph that is going to be compatible with this colors in the points. So the graph will be unitary valent. That means that we will have only vertices with 1 edge or 3 edges coming out of it, and it will be colored. So we will also have some information on the edges of this graph. Ribbon will mean something that we need to detect when we are twisting this graph. I'm not going to define it. And well, the compatibility with this. So when we have this category in a 2 plus 1 TQFT is a functor, as I was saying, from this category to finite dimensional vector spaces and axioms. So one of these TQFT was constructed by Blanchet, Javier, Masbaum, and Vogel around 95. And it was constructed by Sky module and something very, very close to links, and depending in the Kaufman bracket. So I made an exposition of this a long time ago in Sofia. I don't going to review everything of that, but just the combinatorial data. And Eyssidieux-Funar used this construction to obtain the results. And this TQFT depends here. It will depend in a P number in a primitive row for unity. Okay, a lot of data fixing. I will fix even more. Okay, so I want to fix all the combinatorial data that will give me this TQFT. And it's going to be given as follows. So I will fix a set of colors. The colors for us will be just some numbers, some even numbers, 0, 2, 4, until p minus 3. Recall that p is odd. We will fix a genus G orientable surface, and we will consider a finite set of colored banded points. So we will take some points in the surface, and we put to each point a color, a number here. I will also fix a handle body. This is a 3 manifold, such that it retracts to a graph that I will let you know in a second, and such that the boundary is this surface that I fixed. Inside the handle body, we will consider a unitary valent graph. And in the edges of the graph, we will consider two conditions that I will write here that will be important in the construction of this, not in what follows, but in the construction. Okay, and what do I have when I fix all this data? I have the following thing. So I got that the space, the C vector space generated by this graph with all the possible colorings, that is the image of the functor in the TQFT of BHMV. For this P, the functor that I described in the previous slide. And this space is going to be called the space of conformal blocks. So this space is constructed in other ways as well. But here we have all the combinatorial, in some combinatorial data constructed. So it's quite useful to have all this combinatorial, and it actually is one of the TQFT that is most computable. So they can really make some computation on it by combinatorial stuff. Okay, let me tell you one properties of this TQFT. So you have an Hermitian form in the space of conformal blocks induced by a Kaufman bracket. This is a bracket for links in S3, and there is some way of putting a Hermitian form here. Now, we can also define the mapping class group of the handle body, and it will act in the graph. Imagine you have a graph and you make some twisting. You will have some twisting of the graph, and as we have a ribbon graph, something that detects twisting, we can see the action on it. So, moreover, we will have an action of the mapping class group of the surface. Recall that the surface was the boundary, and even if we fix some points in the boundary, if we fix endpoints, and we will denote this representation. So this is going to be the representation that Eyssidieux and Funar used to prove the theorem. So this is going to be the so-called quantum representation, and we will fix this by P. The number P is called the level of the TQFT, and this is going to be the weights I1 until IN. So it has also some other properties that, if we consider an essential subsurface, an essential subsurface is one that, when we consider the mapping fundamental group, it is an injection. So they can restrict to representation of this subsurface in the space of conformal blocks of this subsurface. It's a part of the whole space of conformal blocks. So it behaves well. Okay. So now one of the main propositions in the Eyssidieux-Funar is that this representation, when we have some conditions, they factor to the group that we have defined. Okay. So this representation is not, well, it is a representation of this mapping class group, but it is also a representation of this quotient. Recall that we are also, it's important here that we are considering P odd and plus some conditions here. So it really gives us a representation of this group that we considered before. And as I was saying, this Funar showed that when we have the conditions that Lee asked me in the theorem, G bigger or equal to 2 and P bigger or equal to 5, P is odd, then this representation is infinite. So Massbaum found an element of infinite order, and here they completed some cases that were missing. Okay, and as it factors by here, obviously this representation is infinite in these cases. So recall that we have the Riemann exact sequence, and we have seen here that we have infinite image by this in this mapping class group. So the next question should be, if we restrict to the fundamental group of this surface, do we still have the infiniteness of the representation? And then the answer, quite recent answer, is yes. So with the same hypothesis, plus this one, my one is not 0. This representation, it's infinite, and moreover, it contains a free non-abelian group. So okay, so if you see, this is the statement that I had in the previous theorem. And now let me see some consequences of this representation. Well, of course, that if it factors, then it will be infinite. Sorry, this group will be infinite if the representation is infinite, of course. And moreover, this representation, they also factor by the quotient that I introduced before, by taking the p power of the simple groups. So we have the infiniteness of this group, and for g bigger or equal to 3 and p not in some elements, and this will give the infiniteness of the group in the Bogomolov-Katzarkov surface of the image of the fiber into the whole group. These methods can be applied and to show that over these conditions, this group will be actually infinite. I want to remark here that in the original paper of Katzarkov and Bogomolov, they suggested that it could be infinite. Then it didn't have a precise notion of where the infinite, so they make here very precise. Okay, so now again to the question of Lee, what happens in the other cases? So Humphreys, he showed that this mapping class group, this quotient, is finite when G is greater than or equal to 1 and N is lower or equal to 1. So in very specific case, this mod 2 is finite. So this mod 2 will be also finite in these cases. And so not here that the whole group is finite. And here, where I prove that the image of this quantum representation is finite for every G, and here for G equal to for the level 12. So in the first cases that I was showing, the image is finite. So as we saw, we really needed the representation to be infinite. So now let me say a word in the even case. All the things that I've said before was for P odd, but we have also some results for the even case. Just that this is more complicated. We need to fix also some data, some colors, and the colors satisfying a condition. So when we consider P bigger or equal than 10, recall that in the odd case, the representation factors by the mod P. Okay, but here we need to to consider the simple curves that we have into something called separating curves and non-separating curves. And each curves we will need to make some to some power, some different power. If all colors are even, in general, it will factor only by this. So the root stack construction for equal t need to be changed in this even case. Of course, the root stack works for non-equal weights, but I just wanted to fix the equal one. But in the even case, we need to modify it. We need to put some weights in different divisors. So they have also some infiniteness result for the even case. Recall that we made first the infinite result from the mapping class group, and then we passed to in the Berman sequence to the fundamental group, and then they can show that it also contains a free non-abelian group. So as before, under some conditions of P, they show that this Bogomolov-Katzarkov surface comes from a global quotient of a smooth projective variety by finite groups. So again, we don't leave the world of smooth projective fundamental groups. And the main theorem of Eyssidieux is that when we don't have the weights in all these numbers, the level, sorry, and G is greater or equal than 2, and we don't have this condition, then the universal cover of this surface is Stein. In particular, it's holomorphically convex. Okay, so I think I'll stop here.
Thank you. Is there any question or comment? So may I ask you, what is the role of conformal block in this theory? I couldn't get where you use this theory of conformal block in this case.
So I just called conformal block this space. It's vector space, right? So this is the vector space where you have the action of the mapping class group. So you will have a representation of the mapping class group, this row, in a general linear group.
Yeah.
And you have it by acting in this space of conformal blocks.
Oh, I see.
So that's the role. It is the space where it acts, this representation acts.
I see.
Of course, it is connected in some other sense and interested because
I see. Thank you. And any other question? So then, I mean, let me ask one more question. So you discussed this Bogomolov-Katzarkov surface.
Yes.
But is there any other, possible candidate we need to investigate for among this algebraic surface or 3-4?
I think there are, well, of course, there are some cases remaining, very few cases. I mean, we need to consider these cases for the Bogomolov-Katzarkov surfaces. Maybe in some of them there are counterexamples. Maybe this quantum representation doesn't give the answer. But apparently it's quite difficult to get a counterexample to this. This was the motivation of the work of my thesis. So we studied some branched coverings of P2.
Yeah. And
that ramified along curves, along an arrangement of lines. But it was the same idea. You can do the root construction and this this will encode information of branched coverings. And of course, one thing that makes it very complicated is if you put different weights. If you put not only PPP here, but no matter what, it's quite complicated to say something, even in the case of P2 with an arrangement of lines. We don't know if the orbifold is uniformizable. We don't know if the fundamental group is residually finite, but we don't have essentially a way to study that. So, but of course there are some ideas here that are left, but they seem to be quite complicated. There is another case that I don't talk about here. The Bogomolov-Katzarkov surfaces are not constructed with a stable fibration, but only with a fibration with double points. So there are some cases that are missing here. They are treated in the case of Eyssidieux-Funar, but I didn't want to talk of them, and it doesn't cover. They are not stained universal cover. They are only holomorphically convex of some of them. But yes, there are still some possible candidates. But of course, this I don't know, this shows that most of these surfaces are not counterexamples.
I see. Then how does Shafarevich conjecture behave on the blower? I mean, if I blow up something, then fundamental group I think doesn't change. But then can he still? I mean, if some surface satisfy this Shafarevich conjecture, then can I say that to the blown up surface too?
I mean, I think in the linear case, yes, of course, as you are saying, if you have a linear group in a projective smooth variety, if you blow up, it won't change the fundamental group, so you will still have a linear representation.
Right.
So
well, in general, you know that, or I mean,
no. I mean, I suppose that it's true. I don't know, but as it is very related to fundamental group and it doesn't change, we don't expect to have a counterexamples. Actually, we were searching counterexamples not in the projective case, but even in the quasi-projective case. And in the quasi-projective case, the blow-up is quite useful because if you have let's say P2 in a divisor in P2, you can remove this divisor, and then you can see the fundamental group of the complement.
Right.
But if you do blow up in this divisor and you remove the strict transform of the divisor, not the total transform, the fundamental group will change. And you will have some quotients. And it is more or less the same, because if you blow up a smooth point and you blow up a lot of times, you are actually making this kind of constructions. You are taking a meridian and quotiented by a power P. So you are like doing some root construction in some sense. So this root stack is kind of an intermediate step. If we consider here P to be infinite, if we allow it, we remove it. So we are considering quasi-projective surface. And so this in the quasi-projective case, the blow up really helped to construct. Case.
Thank you.
Yeah, no problem.
And this holomorphic convexity is this something related to? I mean, if this holomorphic convexity holds, then can I also say something like this image of P1 or elliptic curve in this?
The what? The
image of curves or image of elliptic curves in this?
Initiable? I don't get
image
the word.
of this curves, rational curves, or so there are some other convexity in complex geometry, like
Okay.
yeah. Is this holomorphic convex? I'm sorry, I'm very ignorant in this.
No. I think I don't know that.
But I see. So I mean, is this kind of thing can be used to say something about, you know, this Bombieri rank conjecture or something like that?
I don't know.
Oh,
sorry. Yeah.
I see. Thank you.
Okay, no problem.
Yeah. Is there any other question or comment? Okay, then let's thanks to the speaker again.
Thank you.
Okay, so yeah. So to be honest, we haven't fixed next week's schedule. So, but I will announce if there is seminar next to Friday. So anyway, yeah, we will resume maybe in 1 or 2 weeks. Okay. Yeah.
Thank you.
Yeah. See you. Thank you very much. Thank you.
Bye.
Bye. Yeah. Thank you. See you.